Hello everybody, I'm Mia, and I will now present, so thanks Suvi for the warm-up, and now I will a little bit present what's inside the main results in Czech, and then of course afterwards we will then hear these individual technologies, so it will be super exciting. So one of my main point here is, as said, review the main results, what we have achieved with these simulations and digital modeling, and then also tell a little bit about this future-proof vessel design platform, which was mentioned. Also, I have to give a warning for a very turbocharged presentation, but I will walk you through the main points here, so you don't need to focus on every single number and detail you will see here. First of all, the modeling in this project, the digital modeling that we were working with. So it was actually done in several generations. So there's a certain time perspective here, which is illustrated here. So we started with so-called digital prototypes, evolving into digital master round. And now we are finally in this, let's say, digital twin round or past that. So we have the final results. And that just means that when we started the project, so we were working with this, as we heard, 2 case vessels. So we have a cruise ship and we have a bulk carrier. And the first model generation were very largely based on actually measured data from the ship. So actually measured propulsion also. And then the models made, we were starting to, let's say, look at new engines, for example, and taking some technologies there. But then the second round, the digital master, included already new generated hulls for both vessels, for example. And then the final round then included now more details of the technologies working. So we had received a lot of data from the lab measurements, and also the models were improved. So I will go through some things here. First of all, this platform that we have been working with for realizing these results. So I will walk through those main parts. First of all, the future-proof vessel design platform, it's not actually one tool, but I would rather say that it's a combination of different layers because there's a lot of dimensions in design. It depends what we are focusing on. We utilize these same tools in every, let's say, project, also for retrofit projects. That's also the purpose of this development. So we see the kind of 3 main layers here. That's why it's part 1, because now with this part of the digital tools, we are producing these emission and energy saving results en route for these 2 operational vessels. So the first dimension is, I would say, something that we understand best as the traditional ship design. So the ship, let's say, volume and structural model, including all the layouts and all the stability reviews and all the naval architectural analysis. Then the second layer, which we are focusing mostly here in the Czech, is the 2 final, let's say, layers. The second layer is the operational layer, we call it Deltamarin. So that includes actually all the operational first details of the vessel speeds and drafts on various routes, but then also let's say we collected weather data. So that layer actually is taking this digital hull swimming in vacuum, so taking it and combining it to virtual seas. So there is weather data, so there are external forces influencing in the ship, and especially when we are working with this wing sail, let's say, supported bulk carrier. So it means that there's a lot of force balancing that we have to do. Now, as I start to sound like Obi-Wan Kenobi, so I can point you to our master in this. So we have Arun Krishnan, who has been working, our hydrodynamist, with developing this latest code, because we've had, let's say, the basis of this platform for Deltamarin, but now it's further developed for this project. So there's a lot of new coding, of course, we had to do, because we learned a lot about new technologies and how they work. So that's about Deltamarin. And then the third layer is our system level energy simulation layer, where we then combine all the, let's say, energy consumers, such as the propulsion, which is coming then from this operational layer, but also all the other energy consumers, heating needs and hotel electricity needs. And then also we are combining the machinery components and all the interactions between processes and any energy saving devices we have then on that machinery side. And then we calculate the fuel consumptions, the emissions, and all that is related. So here's also a snapshot that of the certain logic there, because it doesn't only, in order to actually model how the ship machinery works, so there needs to be, of course, a logic also. So we have to have actually some kind of power management logic within our model, and that includes when we introduce batteries, it brings another, let's say, element of complexity. When we have waste heat recovery, for example, where we produce electricity from waste heat, so that is actually then reducing the needs for powering the vessel with the engine. So all of that is here, and then we have our master in that, Bogdan, our energy team lead. So he has been in charge of that. So these are the tools, and then we have for this digital, let's say, digital twin round. So we had one more, let's say, addition in our energy model. So that actually included for the bulk carrier with Wärtsilä. This is a cooperation with Wärtsilä that Wärtsilä actually developed an own, let's say, simulation model which balances or it optimizes CPP propeller pitch, gearbox speed, and then the engine efficiency together. So they have this kind of model which eats some of our outputs. So we have been then taking that model and integrating it into our energy tool. So this is kind of what we have in check. And with these ones, we are now generating the results. So already a lot of interactions there. Well, then we can look at these simulated technologies. So for both ships, so we were studying this ultrasound anti-fouling, and then air lubrication, waste heat recovery, and then also shore power enabled in every port. So those were for both. And then for the bulk carrier, there is a own set of things. So we have this flexible machinery consisting of 4-stroke engines and including CPP propeller, including the shaft generator with the possibility to have the power take in. So we can also then produce, let's say, boost the propeller shaft. And then we have also batteries as spinning reserve for this vessel. Then we have the wing sails, gauge rudder studied, and also studied the possibility to, let's say, save energy with solar panels. And as the final decarbonization means, so we have liquid biogas as fuel. For the cruise ship, so we are studying, in addition to these common technologies, so one of the major things was study hydrogen machinery, so hydrogen-fueled engine and machinery. Then there was waste to power concept, also studied on a feasibility level, I would say. And then a large 10 megawatt hour battery pack, including a little bit more than just spinning reserve. So that was a more active, let's say, active battery. And all of this thing, as mentioned already, on realistic routes. So we actually picked these routes from commercial, let's say, operations. So the cruise ship operation is based on a 7-day Mediterranean cruise. That's what we have been using to generate the results. And what I can say here already is that the speed actually of this cruise is quite slow. So there's, of course, we have a lot of technologies like the air lubrication and waste heat recovery, for example, which actually benefits if we would have more speed and therefore more powers and more heat available. So all of this, everything is interconnected, which we will see. But then for the bulk carrier, so we had actually 9 routes in total, global routes, commercial routes, and then the operational profile was developed together with Wärtsilä routing tool for those routes, and then it was run. Each of them was run 12 times with the past historical weather data, so that we'd get a realistic spread of the, let's say, these external forces. So it was a large model. And then we go to technologies or the results. And since it is a busy slide, so I'll walk you through just so that we see what we have here. How did we run the results? This is now for the cruise ship. So first of all, since the project was defined so that we are comparing our gained results to baseline, EEDI baseline. So therefore, this is now what we are comparing to everything. So what we did was that actually here we have the so-called baseline ship. So this is the ship which has our hull, and then we simulated with HFO fuel as baseline without any of these additional technologies. And then this EEDI scaling was done, of course, scaling backwards just to get the baseline to compare against. But then starts the, let's say, energy saving on the HFO machinery. And these results are now presented so that we simulate each round with bringing one additional technology there. So we can just see that the energy consumption is reduced. So on the upper row, we see the fuel energy consumption. And then we see also when we bring the hydrogen machinery in. So we can see that, of course, there's some impact to the energy as well, but most of all to these emissions. So they are getting very, very low, and as we already heard then from Suvi's presentation, so at the end of the day, the results that we gained compared to this scaled baseline is that we are reaching almost our 50% target with the cruise ship, and then the emissions are in practice almost zero because we have the hydrogen machinery simulated now on this energy level. We didn't start to design an entire ship with these hydrogen tanks at this project yet. But since time is otherwise running out, so I have to go already to bulker technologies. So same thing for the bulker. So what we see here. So here we have now on the left side, we have the energy saving, and then on the right side, we see the emission reduction. Again, we had this baseline scaling as the first one to which we then compare everything. And here what we can point out is that actually there is only around 8% change now towards this EDI2 scaling. So this is the baseline ship from which we actually then started to generate these simulation results. And here it's again, this is now actually a result set, which is not, it's not building, everything is not built on top of the previous round, but it has a certain set of individual results and then also certain combinations. So this green arrow is now indicating where we bring in this 4-stroke fuel flexible machinery and the shaft generator. And we see also that the energies, let's say, energy consumption is slowly reducing. When we bring, there's also one result set here, run first with shore power alone, in addition to this 4-stroke machinery, and then also looking at the organic Rankine cycles, and then introducing a combination of them. Then we have also result sets with the air lubrication and the sails, first tested alone. And then when we look at actually putting all of these things together, so then we also see that we are reaching what we have been really focusing on this project check, which we call these technology synergies, that and here is, for example, visible in that sense that when we introduce these energy-saving technologies, including the sails and the air lubrication and the waste heat recovery, and also this ultrasound anti-fouling, which we expect also to actually bring considerable reductions of energy during 1 year. So when we bring all of those together, so it actually would enable us to install a little bit smaller main engine and therefore giving us better engine loads, and also it brings added energy saving with the exactly same energy saving technologies. So that's kind of what we call these check synergies. So so the check combo, as we call it, so already we are reaching quite big energy savings there, around or over 50% compared to this our first baseline. And then when we bring this biofuel there, so in Project Check we have been now calculating it according the emission reduction on a well-to-wake basis with this European standard. So definitely reaching our goals there. And I could also point out some things. Here's the bulk carrier, these main results, what we already saw. So we are having this 52% energy saving, or 53 almost. And then, well, emission savings, definitely mission accomplished there. But here, for example, we can just, what we get when we do this simulation, we run the operational analysis and we do the energy simulation. So I think it's also visible in every way, this energy saving. Here we just see in the pictures, we have on the left side, this so-called baseline ship without the technologies. And then on the right side, we have the check combo, so including many technologies and this fuel flexible machinery. So we can just also visually see how the, let's say, engine powers are shifted towards lower loads in all kind of operational cases. So yeah, there would be a lot more to say, but I could also bring another synergy example now from the cruise ship again. So this was just, I'm not sure if you noticed it, so that's why I brought it here as well, that when we now start from this simulated ship baseline, so not the EEDI scaled. So when we look at this combination of technologies, including the shore powers and air lubrication and waste heat recovery and so on, and anti-fouling, so then we get certain energy saving, around 21% here. But then when we run the same technologies with the hydrogen machinery, so actually then the energy saving, when we kind of just look at purely energy level, so we actually got some additional savings, and the reason is, in this case, all these engine loads and the engine sizing, so it's and the efficiency, predicted efficiency, that contributed a little bit to the energy saving. But then also, when we have a clean fuel compared to HFO, so the ship needs less heating, it needs less boiler heat, because when we have shore power for cruise ships, so then the boiler consumption is increased otherwise if you don't do anything. So that is one major contribution. Also, when we have this hydrogen machinery, we have much more waste heat available for the waste heat recovery, so we can actually use more Climate organic Rankine cycle units. So that is also, I would say, another Czech synergy example that we could witness here. Yes. And then just to mention, not to go to any details here, but one point of the project is not to only decarbonize these 2 Czech vessels, but to decarbonize everything. So in that sense, we also tested a little bit this future-proof vessel design platform, the tools that we had already now applied to our case ship. So we took 2 different ship types. So we took a ropack ship, and then also we have a tanker. So we ran some of these energy-saving technologies and some alternative fuels, and we, for example, we picked Deltamarin. We design all kinds of ships, so we picked one of our ropax designs, and then we put that ropax to sail to actually 2 existing routes. I think this is maybe the color line route, this Norway-Germany. So picking some AIS data points and putting that ship to sail there, and then we have one route in Italy. And then we just saw what happened and testing some methanol fuel and ammonia fuel, and we could then observe the also pretty ambitious energy savings, 20% energy savings with this chosen combo, and then of course emission savings worth a lot more depending on the fuel. But that wasn't it. Our future-proof vessel design platform got to a new level during Czech project when we introduced this life cycle assessment. Since there will be an entire presentation about that, so I don't have to then focus so much on those results. But what I think is worth mentioning is that with these tools, when we simulate the ship in this digital environment, realistic operational profiles, so actually that data about the fuel consumption, if we extend it to assume that this is, the profile the vessel will be operating during its lifetime, or then we choose some other profiles for the future operation. But anyway, that is an input to the operational stage of the life cycle assessment. So then we have also now developed together with, it's like hand in hand with VMU, developing this assessment with Shipe, our LCA star there. So we have been then working there together applying just a commercial tool according to all standards for life cycle assessment. And that means that when you actually then kind of upgrade this operational data with then information about the ship dimensions, certain key dimensions and shipbuilding impacts, the materials utilized during ship building, the energy use, and also the fuel pathways. And then during the maintenance phase and end-of-life stages, for example, what part is recyclable. So then we actually can, what do we have then in our hands as a result of this is that we can actually then predict for, let's say, new design that we make and or the variations, like when we do these choices regarding technologies and regarding fuels, so what could be then the life cycle impact of that vessel. So I think that's a pretty like powerful knowledge for like strategic fleet planning, for example. So therefore, I would just simply like to summarize at this stage that this decarbonization of shipping, as we know, so it's definitely a combination of good operation, efficient operation, and then this technical efficiency, including the technologies and good design, and then the low carbon fuels. So obviously for doing that, so we have to actually consider all of them also during the design. So therefore we have to utilize these kind of tools that enable us to analyze the ships in their realistic environment. And then, as said, so when we add this kind of broaden a little bit our views to this life cycle, so then that is actually a pretty powerful way to kind of guide us that where should we go in the future. Because I mean, if we have these hydrogen ships running there in the future, so then of course the focus of the emissions is switched more to the shipbuilding stages and also the production of the fuel. So in that sense, it just gives us like a good understanding of the true, let's say, decarbonization impact. So with this one, so I would also like to thank you. First, thank our team, because in addition to these masters that I mentioned, then we have our Polish team who have been really sweating with the operational data, and Greg has been doing all the stability checks for our bulkers. So big thanks, and big thanks to you who are all awake. I see